Hello. In this video, we are going to discuss a bit about artificial satellites. Now, we know about the natural satellites which are there, such as the moon that we have. There are many moons for other planets as well. But scientists have also been able to make or place man-made satellites which are revolving around the Earth as well as the Sun as for various purposes for the study and study of various things such as the magnetic fields or even the weather and everything of that sort, even for the broadcasting purpose. Now, the artificial satellite in case of Earth is one which is taken up from a certain base station where it is propelled and it is taken to a height and then it is set into an orbit just like this. So this is the Earth, and the Earth of course has a radius. Let's say the radius is R, capital R, and from that surface it is propelled. The propulsion takes it to a certain height, supposedly say h, goes through a height h, and at that height h, it this is the point, let us say the point is P, and at that point P, what happens is that it is then further propelled and propelled with a velocity which is which sets it into an orbit. Now this is set into an orbit, and the velocity corresponding to that is known as the insertion velocity, VI, V subscripted with I, and from there on it is set to move along the orbit. Now the orbit is it can be a different not necessarily a circular orbit, depends on the purpose in which we are going to use the satellite, right? So we'll be discussing various roles of the satellite, or various ways in which the satellite may orbit around a given planet. Now we have already discussed about the planets and the sun, where the planets revolve around the sun. The concepts that we are going to use in this case will be the same for sure, because they are we are concerned with the central mass and the central force system, and the two bodies, that is the planet and the satellite, they constitute the two body central force system. Now this insertion velocity vi, with which it is set up uh, to orbit around a given planet, at that point P, if we consider the energy relation, now the energy can be given as the total energy, that is will be comprising of the kinetic term, which has the insertion velocity vi squared, and then we have the potential energy, which will be in the negative form because of the gravitational attractive force, the work done by it, and the distance, total distance in that case, is obviously taken from the center of the Earth, that is at a distance r over a height h, so the total distance is r plus h. Now the orbit will be a parabola or a hyperbola or even an ellipse, which is usually the case, and it depends on the value of E. If E is let's say 0, then it'll be probably we had discussed the conditions actually, where the values of E determine determine the shape of the orbit uh, that we considered in the two body systems, where I'd mentioned that E greater than 0 results in a uh, hyperbolic structure or conic, and then we have for E is equal to 0 we have a parabola, and for E less than 0, that is negative value, we have an ellipse. Now for this, usually the case is for elliptical orbits, and therefore for elliptical orbits we must have this term to be less than 0. in case of an ellipse, where the planet obviously lies in the focus, the center of the planet, that is the point, let us say the point O, that lies, that is the focal point, and the satellite, it orbits around the planet. Now from this relation, what we get is that this half mv squared or vi squared term will be less than this term, that is gmm divided by r plus h. The m's can get cancelled out, and we therefore have vi squared to be less than 2 times of gm divided by r plus h. So this is the condition that we are getting in terms, in case that the total energy is negative. Now the total energy determines the size of the uh, semi-major axis. Now the shape, however, is the eccentricity of the orbit is determined by both the total energy as well as the angular momentum. If you remember the relation where we had obtained in case of the two-body system involving the central force, where we had the eccentricity to be equal to 1 plus the eccentricity gives the shape to the orbit, and so we have the relation where E is equal to 1 plus 2 times of E j squared, which j is the angular momentum here, and m k squared, where k is the constant term that is associated with a given kind of force. Now, it has already been discussed earlier that the energy term that completely depends on the uh, major semi-major axis, value of the semi-major axis, where we have the relation E is equal to minus k by 2a, and as for the angular momentum, we have the value to be equal to mv square. In this case it is vi squared times of the square of the same major axis, where we have the same major axis to be a squared. Now, a here is going to be is equal to r, where r is, we can take this entire distance as small r, where small r is equal to the r plus h. So this is mvi squared r squared, which is also equal to mvi squared r plus h squared. Now these values that we are getting, what we have with us is that the eccentricity, if it is 0, then we have the orbit to be a circular orbit. So for a circular orbit, we have the value of the eccentricity to be equal to 0, and therefore what we have is that we can square the term. So we have 0 on the left hand side, square of that is resulting in 0, and on the right hand side we have 1 plus 2 times of E. We can put the value of E from here, that is equal to minus k divided by 2a, and then we have the value of j squared, which is j is, well, j is mvr, so this is j squared will be m squared, v squared, and r squared. So m squared vi squared, and then we can keep it a squared for now, and this one in the denominator we have mk squared. Now one of the k's can get cancelled, and the one of the m's can get cancelled as well. So is the case with a, they get cancelled as well. Now with the negative term, we can take that over to the other side. The 2's get cancelled over here, so we take that to the other side, and we have a positive value, that is m stays, vi squared, that also remains, and a divided by k, that is all we have. and over to the right hand side we have the value 1. So now we have vi squared, that is the insertion velocity, insertion speed, that is to be equal to uh, k divided by ma. Now k, as you know, for gravitational field we have g m times of m, and this is m as well, and a, as we had mentioned, is r plus h in this case. So the m's can get cancelled out. We are left with the insertion speed, square of it, to be equal to gm divided by r plus h. So it depends on what height we are taking the satellite to be. At that point we'll be determining the insertion speed, and we'll be inserting it into the orbit of the around the planet. Now the insertion speed is usually in kilometers per second, nearly at a height of, say, h is equal to 10 kilometers. We have the insertion speed to be nearly equal to 8 kilometers per second, and this was the speed that was achieved by Sputnik 1, which was projected by Russia, and it achieved that speed after completing the 3 stages of propulsion. And but that's a topic that you can see for yourself over the internet, or you can browse through the networks and you can obtain those historic datas to comply with the calculations that we have just shown in this video. Now, from the case of satellites that we have achieved, which we have studied till now, we would also like to discuss a bit about their purpose. Now, the purpose is something which is essential, and that is why they were made. Now, we have the form of geosynchronous. Geosynchronous, they are the orbits. The geosynchronous orbit is the orbit that is for a satellite, and in that, if the satellite travels in that orbit or orbits in that region, it simply maintains the time period of rotation around the Earth. So the rotation around the Earth, the time period, that is, the time period of rotation around the Earth, that is equal to the rotation of the Earth itself, which means approximately 24 hours, 23 hours 56 minutes and 4 seconds to be precise. So this is nearly the same time period in which the Earth rotates about its axis. So this is in sync with the rotation of the Earth, and therefore it is a geosynchronous orbit in which the satellite must move. Now, this can be easily determined by the Kepler's third law, where we have the distance for the satellite, we take it as as, and we know that the value from Kepler's third law, that is, we have t squared is proportional to the cube of the semi-major axis. And here the semi-major axis for the satellite that we are putting as AS, so the cube of that is proportional to the time period, and we have the value of the orbit the square of the time period, that is, and from that we have the value of the orbit AS to be proportional to t 2 by 3. We know the value of t, that is approximately 24 hours, and we put that value, and from that we can calculate usually the case of satellite that we have calculated the value to be approximately 42,165 kilometers. So that is usually the value that we associate with the geosynchronous orbit. Now, in order that now this geosynchronous orbit obviously has can have any kind of eccentricity. There is no compulsion that it needs to be in a circular orbit. It can have any kind of eccentricity and any kind of orientation with respect to the equator of the Earth. Now supposedly we further have a condition. So this is any orientation with respect to the equator, and this is any eccentricity. It doesn't really matter. A special condition, however, we have the special condition for my bad special condition that we have for from the geosynchronous orbit is the geostationary orbit. Now the geostationary orbit is must be a geosynchronous orbit obviously, but it has to be stationed over a particular point. Let us say a point over the equator. It has to be stationed over that point, and therefore the eccentricity must be 0, which means the geostationary orbit must be circular. It has to be circular. It has to be geosynchronous, obviously synchronize itself with the rotation of the Earth, but the orbit must be circular so that it stays over the place, over the geographical point, over the Earth. And usually this is calculated in terms of the height that we have. The height is AS that we have calculated to be nearly 42,165 minus the radius of the Earth. Which relation are we were using this relation, so this is the relation that we are using. R plus H is equal to A, right? So we are using that relation. So AS, that is the semi-major axis, minus the radius of the Earth, as we know, is approximately 6,400. So 6,400 subtracted from that nearly results in the value. This is also an approximate value, so the approximation continues with this. So this is nearly 35,790. You can calculate that. So nearly 790 kilometers. So this is the value. This is the distance above the surface of the Earth where the satellite must be stationed, or station means it must be in that geosynchronous orbit with a circular of course with the orbit being circular. So that's more or less about the satellites. The usage obviously is pretty simple. They are commissioned over there so that we get the broadcasting, clear broadcasting, and as well as to check the weather conditions, especially in the upper atmospheres, for astronomical observations as well, and various measurements relating to the fields involved in the Earth's gravity, maybe the gravitational field as well as the magnetic field, Earth's magnetic field. So this was a simple video on related to artificial satellite. We'll be continuing with the two body central force systems, where we'll involve the case of scattering in the upcoming video. Till then, thank you for watching.